Now, let's continue the third part of the tutorial. Emergent universal Turing machines in DN, vision, audition, natural languages, APFGP, and thinking. Lobe component analysis. Let's look at what each neuron is learning in a Hebbian fashion. So maximum likelihood in n dimension. N is huge. The n is number of parameters inside the brain. Suppose Weng team. And the contact input of each neuron, you have a pixel, muscles, and hidden neurons. This dimension is huge. And the number of neurons here is Weng team. And plus pixel plus muscles. And this is still the largest one. Neurons are spawned incrementally in the DM. And from small to more, starting from small. And each firing neuron update locally in maximum likelihood when it wins. And probability density, it's a vulnerability requirement, but vulnerability requirement is very rigid, only top one firing. Here you have committee voting situation, so you have a top K neuron firing. It's kind of for local, but multiple committee members vote. And your minimum average distance from voters to each neuron. So basically, the maximum likelihood is like neurons that move to the location that's have maximum likelihood, and when they move, their distance from the voters, from the current input, is minimized. In other words, it will estimate the best step length based on the confidence you already accumulate from the past learning experience. And what the feature it learns, it's not Euclidean distance, and actually it's based on the principal component analysis. Suppose we have a principal component analysis as a framework, and this is the feature one, lambda, and this is the feature two, V1, V2 are features, and this is the standard deviation on the feature, standard deviation onto the based on the zero mean inputs, right? And this is the measure axis and measure. Suppose if the feature are all solvable, later on we'll give up this requirement, we'll relax that requirement. So feature one, feature two, and we want to find the feature one, feature two, so that the area of reconstruction, reconstruction from the area one, feature two is minimized. But the dimension has to be lower, right? Here, suppose I have a 3D example, we have 2-dimensional inputs. So it's like a disk, and you want to find a disk, you want the longest axis, second longest, and then you have only two, then the third axis to be shortest one, so that you minimize the lost energy. That's a principal component analysis idea. But the dimension right now, it's not just 3 and much higher, all right? And the feature space could be like 50 or 100. In dimension could be thousands. And the CCI is candid, covariance-free incremental method. We want to find the principal component analysis. This is batch, and we want to do incrementally. Input of these dots, these input dots coming incrementally as X and incrementally. And we do CCI PCA using incremental computation of the mean. And then we do compute the scatter vector from the incremental mean, and this is scatter from the mean. You do incrementally, everything incremental. Then you compute the pre-response, normalize the weight vector, multiply the U. U is the scatter vector here. Then this is the retention rate, is the learning rate, response weighted U, and this response is the how well you are matching, all right? And response weighted input, then you update your weight. If you do that, it proves that you get principal component. V become principal components. The first V1 will become principal component of all the samples. This is the learning rate, is the retention rate, and because the data comes in incrementally, we want to increase this a little bit. If you have this equal to 0, then you have street average. Street average is best if you have you don't have change of distribution. But in fact, we do have change of distribution because the V changes. All right. So we want to increase a little bit so that becomes positive. Then you give more weight to the newer data. Then you have less weight for the older data. But the W1, W2 retention rate and the learning rate will become 1 all the time. Then you compute the residue of the remaining error components. You go to next feature. This U plus 1 will be for V2, all right? And V1 and V2, you know, I equal to 0, then it will be V1, V2. And you get also the feature vector coming in CCI PCA because all the principal components of the CCI PCA has to be orthogonal. And this is the key to find orthogonal features because the observation for the next feature is orthogonal to the first V. Do you see that is the first V? The DM1 algorithm runs like that. Input area XZ, output area XZ, and the dimension and representation of the XY areas are hand designed based on the sensory factor of the species, depending on how many pixels, how many muscles, and why is skull closed inside the brain, not directly accessible to the outside world. And then for time t equals 0, for each area A could be X, Y, Z, you initialize the that part, N, this is the vector, and H actually. And later on, we'll have a weight vector and an H, and also have a connection patterns, right? And the this is related to synaptic maintenance later on. We'll talk about the connection where you connect it, all right? Not just input vector and weight. The response vector R, where V contains all the synaptic weight vectors and G stores all neuronal age in this case. Later on, we extend it. For example, use random weight vectors, 0 ages, and initial responses, or the generative DM method described below. At the time t equal 1, 2, for each area A in XYZ, do following step repeated forever until you have death or body death. Every area A perform mitosis equivalent if it is needed, use its bottom-up and top-down input B and T respectively. So basically, A may split neurons. Mitosis means split, all right? Otherwise, once do mitosis, then the new neuron using your bottom-up and top-down input B, the same, but age is 0. Every area compute the area function. B for bottom up, T for top down, the adaptive part, and area function will map to the new response and the new adaptive part. The R prime is the response vector. I will talk about the area function later on F. And compute this way. This is just like we did before. This normalized bottom-up energy and the normalized top-down energy, and you become the inner product. You add these two together, and the pre-response range from -2 to 2. And then to simulate lateral inhibition between the neurons, we use a winner takes all. Later on, we do a little more better. Just do a simple version first. This is DN1. Within each area, you top K files and consider K equal to 1. It's simpler for us to understand, but the same principle carry out for K larger than 1. And you find the maximum response. For all the neuron I between 1 or C, you find the highest pre-response, you find a winner. Then the winner will update. Loser will not update. Before we move on, let's look at the lobe component analysis. We will still use this formulation, but then we don't do a required feature to be orthogonal. we drop the orthogonality restriction because neuron between different features don't have to really be orthogonal. Principal component analysis is mathematical but not biological. And lateral inhibition to simulate biological inhibition. And we keep the CCI part, candid, coherence-free, incremental, because brain does that. Brain is candid, does not lose energy. Then the candid coherence-free means that brain cannot compute coherence metrics of the input. Way too many. Brain does incremental learning. Right. So neuron as feature detector in LCA. Suppose I have a neuron that compete. This is black means compete. Hollow means learn. They have 3 pixels, for example, right? Then they have 3 neurons learning, and 3 here, and then it will biologically motivated with the Hebbian learning, and use lateral inhibition, and the 3 cluster will tessellate the input speed into 3 regions, 3 neuronal regions. In this example, 3, 1, 2, 3 in the product space, and a local component I is a principal component of region I. So we only keep the first PCA of that network. We don't really do the second, all right? And we do inhibition to allow neuron to compete, but within each vulnerable region, we do not have multiple neurons. We only compute the principal component, the first principal component of the region I. That's related to the PCA. So the local component in the region is the first PCA of that region. With a different normalization method, you will have a different shape of the local component. Here you have a positive, negative, and the image input is a unit vector. Then you suppose you have 3 regions. Now you have a local component 1, local component 2, local component 3, and the plus are input images. If I have a maximum component to be 1 and others are not constrained, then you have this kind of space. And this is not as good. And we mostly doing this when the norm is normalized. But in this case, we don't have a 0 mean input, then the 3 components like that. And actually we do this one because this is subtract the mean, the content is subtracted out. So dual optimality of CCI LCA is that it's have a dual optimality. You have optimality in 2 senses. One is the spatial optimality, another is temporal optimality. Spatial optimality means that the target, the reconstructed. Suppose you have a reconstructed using the V as a subspace, and this is input. This is the context, X, Y, Z actually later on. We use X, but later on it will be X, Y, Z. Then you find minimum. V is the target, spatial optimality. The target is the minimize the error in the Euclidean model. The stars are optimal. And how to reach these V's from the X? And this V is inside this C. These are C features, for example, right? The temporal optimality means that the best winner to the target, given the limited experience up to time t, find the best direction and step size for the t, for each t from response-weighted observation. So this is the best. We also know the step size, not just direction, not just gradient. Actually, it's the same as gradient, but also step length. And this gradient is different from convolution neural network gradient. That's a global gradient. We are already compete. After we compete, we know this is my job. Then my direction should be the best. And once you have local gradient, is the best in maximum likelihood. So this is a dual optimality, spatial and temporal. And what do you mean by most efficient estimators? Most estimators, the most efficient estimate is the one that has least variance from the real parameters, the sample mean of the data is the most efficient estimator of the mean if the distribution satisfies some regularity conditions. And suppose I have a minimum variance estimator, and if I have optimal, then once the sample comes in, it has a much smaller jitter centered around the true parameters. But if I don't have optimality, then I will jitter a lot more, and error is a lot more once the sample comes in. And the most efficient that this variance is the minimal, is the least possible in theory. And we use top K computation in the DM. So we add mass from the maximum input and continue on the algorithm we had earlier. And the winner will respond with the input. Input is context normalized. This is learning rate, this is retention rate. Winner will be updated old and new. And suppose I have the learning rate depends on finding age, NJ, the finding age NJ of the neuron J, and the retention rate and the learning rate add together becomes 1. The simplest version is that at age 1, and then suppose that age is I, then if I equal to 1, then this is 1, response is 1, and input will feed into this directly, no matter what kind of random weights you start with. Random weights will only decide which is the best winner. But as soon as the 5 first time, the input will get into the weight, and the initial weight is totally forgotten. So no matter who wins, you result in the same network, right? And if you do that one, and here we do not have analytic parameters positive, then you end up with the average. The average by minimum variance estimator, this is the best, is least variance from the true parameters. ML-Optimality of emergent Turing machines, it said that GENISAMA Optimality, by learning from any teacher Turing machine, a regular or universal through patterns with mode 1 or 2, basically using the teaching by supervision or reinforcement or imitation. The top one finding in Y, the DN control enable a learner GENISAMA Turing machine to emerge inside it with the following 2 properties. 1, sufficient neuron situation. Now extended to very much like we had before. Now we talk about the optimality in the higher context. We talk about emerging Turing machine becomes optimal. And error-free, you have enough sample, all right, all learning transition. And distribution of all observed physical experience. Mode 1 means that you have enough samples, and mode 2 is that you do not have enough samples. Then insufficient neurons, then it happens when the finite and Y neurons have all been activated, then the action at time t+1 is optimal in the sense of maximum likelihood, but not error-free in representing the observed context space, motor Z and sensory X, condition on the amount of computational resource and experience of learning for all the discrete times, all right? So these are conditioned on the incremental increase and condition on the number of neurons. Once you learn out the neurons, then these neurons start to update based on limited resource. The next one is auto-programming. Why do auto-programming APFGP? All natural intelligence use APFGP. And over the lifelong experience, so on zygote, embryo, fetus, newborn, infancy, adulthood, and behavior become more and more low-like become more and more smart. And what is minimal set of APFGP through the very big difference in terms of behavior, in terms of size of network. And autonomous programming, we have two learning modes, mode 1, mode 2. Mode 1 is learning from teacher, and mode 2 is learning from real world without explicit feature. As I said earlier, mode 2 is self-generated reinforcement or imitation. And mode 1 is the teacher sensory motor learning. Conscious machine can emerge through APFGP, and I have two papers. One Estimator AIXIV. Although AI is supposed to be claimed and not peer reviewed, but they rejected, actually. They rejected. They said that there's not enough scientific material in it. And then once I submitted to a conference, ICDL Epiroba that was accepted, then I tell archive that this was accepted, then archive accepted. I don't understand it. Why archive has to peer review it when reviewers are not expert and they don't have much time. Grounded symbolic Turing machine, and now I'm supposed to have a grounded. And we have an image coming in, then the top down can win a neuron that pay attention to this patch can win, and you start to pay attention to that. This is the factor that comes in, and you need a body control. This is a robot humanoid in our lab. And GENISAMA Universal Turing Machine is like you do not have a known task. And the regular Turing machine is special purpose, and the universal Turing machine, and this machine you have a program and special purpose program and general purpose program all embedded in the same network. We call DM. Then the DP is, I will talk about DP. DP is the program to develop the DM. Now, give a little bit more detail and how can relate to the symbols, right? Originally we have symbol, we unfold time and more clear analysis. Corresponding to the FA, do you see that? And you have vectors. Then I have two passes actually. Here I do not have lateral inhibition. So here I don't have Y. Do you see that? I don't have lateral inhibition. So Y has a top down, bottom up, but without lateral inhibition from Y to Y. I don't have the Y to Y connection. Then once you get generally this one, and without input, and I need to supervise. The bar means supervise. If we supervise from outside, that's fine. But in fact, later you see that you can supervise yourself because your body, your innate behavior, you supervise yourself, all right? And then this empty set, then you supervise. Once you have supervised, then they start to run. And here you have Y, and this also Y runs, right? Y will generate Z prime, X prime. And the input here at T1 X prime is like that. Then this is like sandwiched, this one, you have two parallel paths going on if we don't have Y to Y input. But here you have only one path, one row. Here I have two rows because they run in parallel if you don't have Y to Y connection. But each input X will get 2 timestamps before you get to the Z. And this context will have 2 time in text before you get to new context. Auto-programming theory. Said that a GENISAMA Turing machine inside DN automatically programmed for general purposes. General purpose is called the T test. I went to any number. After it has learned a universal Turing machine, TU. Actually, this universal, it's not a single, actually. It's always incrementally, this universal Turing machine becomes more and more mature, right? TU and the related purposes TI. So TU can integrate TIs. However, the DN algorithm, DN itself is task independent and the language independent. For example, it uses native language, could be English, Chinese, computer language. I can write a program DN, and that DN can learn other languages that I'm not familiar with. So let's see how it learns, all right? Suppose I have a FA like this one, and double circle means accept. This is FA. Then I don't have symbols here later on. I have an ABC symbol and a 0, 1, 2 symbol, and I have if I have A, 0 input, I have A state, next state. A, I have a 2, I have a next state D. C with 1 input, next state D. You can see the transition. This is like that. This is a diagram way. This is the table way, and the computer looks this way. Computer did not use a diagram because it did not understand diagram. This is for human to understand. This is for machine to run. The next one is a miracle. We want to change this one to pixel. We change it to muscles, and this become muscles. So let's do that. This is the one we had before. That one here. I do it here. All right. Then I replace everything. Input become pixels, binary, simple, and the muscle become binary, like a spiking neuron model. Then this is the transition table, just vectors. All right, then what happened? Because Z is representing here, X representing pixel input. Then I start to have a first vector, and I have the Y as a feature. Y will, first neuron will remember, first neuron will remember the pattern. The neuron will represent the remember the this pattern. Top down input is this pattern. This is why when we remember this pattern, then we link to this is the transition. This 0, 1 is this one. Then next neuron will remember this pattern, top down, bottom up. Then link to this one. 1, 0 will be here. Here, see that? Then this one, Y3 will go to this 1, 0 will be here. See that? And I keep going like this. This is one way. So that emergent. So the DN will learn the FA like that, vector FA transition table, one transition at a time. And I will remember the Y1, Y2, Y3, Y4, those are the hidden neurons. Revisit Billion problem solved, all right? And the frame problem, the linear control problem, cost dimensionality, local minima, optimality, post-selection. Then we start to do Y-to-Y connection. That's our DN2 for better thinking, all right? And a comparison among machines, you have a Turing machine, UTM, robots, prior neural networks, GENISAMA Turing machine was the only one that can do auto-program, all right? And Emergent prior neural network can do partial emergent, and GENISAMA can. So you can see this is a huge advance in terms of concepts and the capabilities. So don't just say, I only care about engineering problem. Engineering problem, you keep doing this one, keep doing this one, keep doing this. You never have fundamental advance. You only have data that's erosion. Motivation. Traditionally, we have two modes of learning, supervised and unsupervised. Supervised, each time t, a teacher supervised the ZT of the learner so that ZT predicts correct state and actions for universal Turing machine for all the times. Another assumption, unsupervised, at each time t, learner self-generates ZT so that ZT approximate state and actions for universal Turing machine for all times. Let's review a little bit the kind of signal transmission in the brain. The A is point-to-point from neuron to neuron that's through synaptic connections. B is hormonal transmission through blood veins and arteries. The hormones are injected into bloodstreams and then released outside of the arteries and veins into other cells. The C type is autonomic nervous system through patterning and gene-regulated connections, and one signal can be sent directly to other neurons. That's through, actually it's also through learning. This one is a lot, has to be experience-based, and this is regulated by patterning, mostly by morphogenes. D is diffused, where you have neurotransmitters that are diffused into the tissue through the glial cells, and then the neurotransmitter will be recepted by neurons. Those are diffused from one source to many, many cells. And we'll talk about this in the next slides. So motivation, you have neurotransmitters in addition to the AMPA, glutamate signal transmitters, or GABA, which is inhibitory connections transmitters. Then you have another 4 types in addition to the basic 2 types: 5-HT, DA, SH, and AE. Serotonin, 5-HT for short, represent pain, stress, and punishment, and so on. Dopamine, DA for short, represent pleasure, wanting, anticipation, and reward. Acetylcholine, SH for short, is represent expected uncertainty. Norepinephrine, NE for short, represent novelty or unexpected uncertainties. Then move on to a Church-Turing thesis. Oh, by the way, I'd like to say that I will not talk about too much about the representation, mathematical representation over here, because I encourage you to read the books by myself that has all the detailed expression how neuron receive 4 types of neurotransmitters and affect that operations. A brain is a Grand UTM, include the multiple TMs and one or multiple UTMs. And the grand transition table suppose to have task 1 and 3, and this is task 1 and this is task 3. And they are originally you can we model that as symbols, but then once you have numeric vectors. And you can also see that they are partitioned by the 2 FAs, and they can call one another once you have vectors. Church-Turing thesis said that a function on the natural numbers can be calculated by a paper and a pencil method if and only if it is computable by a Turing machine. It cannot be formally proven as stated in Wikipedia. And we extended this thesis and proved it. The series said that for any Turing machine, any machine, natural or artificial, the following A, B, C are equivalent in terms of computing engine. A, it's a GENISAMA augmentation learns and auto programs for general purpose in the real world. B, it computes all functions that are computable using pencil-to-pencil method. C, it computes all functions computable by any Turing machines. A and B assume that the machine has successfully learned. C assumes that Turing machine has been correctly programmed. And the proof is that we start from A, then to B, and a C, then back to A. And A, B, C are defined before. A is a grand GENISAMA Turing machine. B is any paper and pencil method. C is Turing machine computable. And this one is intuitively defined by classical definition of a paper pencil method, because it has to do with human. We need to have a model. So A, we have a model which is grand GENISAMA Turing machine. It's extension from paper pencil method. So once we have that, our work has proved that Turing machine computable and additional mechanism will be able to do A. So that's the fundamental advance of the science. C to A is advanced science, and A to B is a special case, and B to C is already proved as a special case. So talk about experiments. Vision guided navigation, you have a complex environment, you have pedestrians, cars, traffic signs, and shadows. And APFGP platform from a startup I helped to create. Its name is also GENISAMA, and where you have the platform, you have a goggle that has a cell phone running and has a stereo camera, and it get real-time stereo video into the cell running on the cell phone running network, and wireless USB connections will take the input from human in terms of the motor signals, and everything is running interactively in real time. And this is the performance evaluation in the 2020. We tested the signal input from the human is disparity, and the accuracy. This is the time pass, then the error gets down, gradually go to about a little over 1 pixels. And for other navigation, where you have a stereo cameras and a general purpose machine, where you have a GPS tell you the long-term path from the Google map, and the camera to give you local information, where you have the walkways and obstacles, and automated integration of all those signals, and a skill from learned experience. You basically take the signal system and for work outside, it's like a baby. Then I handle very challenging environment, and you have like shadows, and you have shadow from tree, shadow of lamp post, and you have challenging lighting conditions. And the at MSU campus, the training in the blue path over here, then the training with internal connections, white-to-white connections. We have red, and purple is real-time testing. So you can see that testing was disjoint from training sections. So generalization is across different physical sections. And the learned concept for recognition, including relevant cars, cross pedestrians, for example, traffic signal, where scale, boundary, contour, that's theoretically possible. But in the experiment, we did not do all. Distractors may including irrelevant cars, building, shadows, non-crossing pedestrians, and a goal could be direction to head, obstacles in the way, contour strategies, detour strategies, and current directions and speed. In experiment, we also did parking, where you can find an empty slot that you can get in and back out. For audition, it's like you have a speaker and you have other speakers, and lip reading is used for attention, and you may have noise. The new thing here is that we use dense context phoneme sequences. And before we use a symbol as a dense labels, but now we don't have labels. That dense sections, it's a context generated by the vectors. Then the label becomes dense. You don't have to use k-mean clustering as we did earlier. Then each context has dense labels, and this is sparse when you have a type at the end. And but another concept one is dense, generated from signal automatically. And we do not use MFCC because MFCC is for human speech only. We want to learn any sound, so that we use a Cochlea learning model for natural sound. And the Cochlea, you have a base, you have a sensitivity to high pitched sound, and apex has a sensitivity to low pitched sound. And we modeled a system learn why to recognize. So you speak and listen to recognize at the same time. The sensory input is dense. So basically the sensory input what you hear. And you hear and you use that to develop a motor area. Then develop muscle action is dense over here, and free of symbols for motors. We don't have to use symbols, but rather the vectors that's learned from the environment and are generated, heard, that they are doing the same thing. So why we do a APFGP for audition? And the reason is that we don't have to really put any symbol into the context, and motor will emerge very much like language. We will talk about that next. But actually, sound is the same thing, and sound is a short form for the language. If you make it sound longer, you will have natural language. In this case, we have bilingual environment, and you have English, French. You may have different dialects for human. You may have a sound signal, and you may learn mother tongues, but mother tongue may have two languages. In this case, we have English, French, and we have a bilingual environment, and over 2,000 words learned, and over 8,000 contexts learned. Context is the meaning. And this DN has 0% error for signal noise ratio from 20 dB down to even 5 dB. Even 5 dB, a lot of noise has 0% error. And if the signal to noise ratio down to 0 dB, which means that noise and signal are the same energy, and the signal, the DN only produce 0.02% of error. This is because this network has abstraction into the context. Give example that I don't and I do not basically mean the same thing to abstraction over here. And once you have abstraction, then extension to in the noise environment can perform reliably. This is a representation of two concepts. Color over here represent meaning, and each neuron was coded by color here. This is internal neurons. Over here, color is a language type, French or English, and the neuron here has different colors. And if it's gray, it means neutral, neutral language. Neutral, that's true for both English and French, like number. And then over here, that the give example here, right? Give example, you have a color here, and this is for meanings. This is a connected means a temporal sequence, and here that means a language type. Number 4, talk about thinking model. This is a general purpose for machine thinking. And the particular example we like to show as a comprehensive thinking example is planning. And the simulation environment so that we can test the performance of the signal using disjoint set and ground truth. And you start from here and navigate around, and this is the target, and once you reach the target, you will have a reward, and once you move around, you will have counting the tile. We will teach the machine how to count the distance in terms of tile, how to obey the traffic sign, which is the blue light and green light, the green light and red light here, and this is the obstacle. And the sensor, you have images that has a color of the environment, and also for simplicity, we also give the direction of GPS. GPS give you the direction. Then you teach these learner as lessons, skill 1 for lesson 1, skill 2 for lesson 2, skill 3, skill 4, skill 5. So you teach each lesson through basic skills. Then you put together the skill together in the long sequence. In this case, planning. You have one plan, another plan, and you decide which plan has a better cost, and the cost was also learned. In this case, is the reach the target and the distance. And we have 3 new maze tested. Success rate is 100%, and the planning result is perfect in this case for new setting. Now this new topic is about unsupervised. Unsupervised, you don't really need to sensory motor supervision. So ICCE conference this year, 3D to 2D, back to 3D. From 3D to 2D, if you teach 2D, is a sensory motor learning because it's 2D images and 2D motor. You supervise 2D motor. And then once the motor has a general sequence action plan, they execute it back to 3D. So you finish the loop from 3D back to 3D. And the theory is that imitation is general purpose, as we will explain here. So teacher in this example that had a hand place a phone on the ear, and the child imitates, also doing a hand places a phone on the ear, and the creativity for the child in this case is teacher becomes self, and left hand become right hand. And if the change is considered creativity, then in the eye of the observer, then this kind of child is creative. If the creativity has a high value, then in science, then we typically called the discovery. Let's look at the formulation using DM. Simple motor, that's early imitation, typically soon after birth. Then in the prenatal birth, we learn the Z innate that has can automatically invoked later as innate behavior, and then associated with sensory event X effect. So suppose that I cry, and I sort of cry, and I hear this sound of myself. Then the sound, when I hear sound and also cry, then the sound will evoke the cry. This is like self-supervised. Then as a baby start to cry, and I hear the sound is like my cry, based on similarity, and I also cry. This is a simulation in the early birth. When I hear other babies crying, I will cry too. That's imitation, because I heard my voice of crying before. And my action supervision during learning is self-generated here. And this is a self-generated, continue. That's imitated from other. We don't need a teacher to impose the action here. And the complex motor imitation is a multimodal imitation capability is a later time extension from the early imitation theory. By extending the Z innate to an early practiced sensory motor action Z multi, and requiring more fine-tuned neuron YM in the neural network that tune their receptive fields to more relevant sensory objects, XZ, X multi, that I also sense from sensory motor concept of the event, all right? So very much like we had before here, except that we use the new subscript. So I practice this one from innate behavior, and I become multi because, for example, I can dance, and then the multi-limbs start to move together, and that will give me sensory inputs. The sensory inputs, I'm doing the same, this is the same time, the sensory inputs will allow me to do this. Then once I see other people dancing, for example, then I will invoke my dancing behavior. That's imitation, right? I need to practice myself. Then other people are doing this one, and I start to do imitation. So this is a refinement, and this may be caused. This will be refined. I look at other dance, and I try to do dance better if you have a value function that's learned through motivation. If an autonomous imitation is for a long sequence of events, the above error indicates triggering the starting context of the corresponding emergent Turing machine that display the event. So you don't impose a motor for certain action like attention. Suppose this is a pay attention to certain parts of the X, like hearing, right? Suppose they say, listen to me, and you pay attention to my voice. It's not supervisable because it's an internal attention in the brain. So this imitation is a key to almost automate the learning for internal actions. So conscious learning is necessary for brain learning and machine learning. And before we saw that we have a brain learning, they have a consciousness. Now we turn the concept other way. You really need a little bit of conscious in order to really pay attention to the brain learning, the same for machine learning. So machine learning needs consciousness as a necessary condition. Then once you have a little bit of consciousness, then the next time it will be better. You have a better consciousness. Your better consciousness will guide to the next learning. So it's like a recurrence. Necessary of the conscious learning also attribute to creativity. The theorem says that thoughts by natural and artificial agent via autonomous imitation of 3D real-world events are of general purpose according to university machines. If the imitation result is judged considerably different from the event observed, but it's creative, such autonomous imitation corresponding to creativity of the agent in the judge's eyes. So we need the grounded, so we have different robots or vehicles. These two are from Flying Fox, AVS. And we like to allow machine to learn autonomously instead of feeding data like this robot, Boston Dynamics. Boston Dynamics did a super job, but their learning is not autonomous. And here it's the fitting commercial car where the company has a comma and the device is a panda. Is interface function has only $200, and device we used as a comma tool that doing lane tracking, and it costs $1,000. And many newer car models are supported by Panda. So in this particular case is a 2021 RAV4. And for education purpose, because these have so many fundamental advances, and it's difficult for many researchers and students to catch up. So we have a BMI Institute and has a program. And we have courses. 803 is cognitive science. 861 for brain automata. 871 is for computational introduction to brain mind, using my book as a text. And each including video lecture, PPT file, exam grading, and BMI course certificate if you've passed the course. And we also learn AIML Contest, AI machine learning context. The first prize is $10,000. It's unique in the sense that task independent, and you don't know the task. You need to use the supplied engine, or you can use others' engine if it's general purpose. And it's modality independent because test has 3 modalities: vision, audition, and language. And for students, full-time student, only $50, including 3 courses and a workshop for coaching and 1 contest entry. And for 2022, there is a call for proposal currently is open, and the machine conscious learning project starting from summer or fall, it's up to you. And we can start as soon as summer. And the deadline of application is January 15. That's about, let me see, today is 36, so we have about 9 days. And the student teachers are jointly paid if they are supported, admitted. Students, including grad students or undergrad, teacher, including university, faculty members, research lab researchers, or industry product developers. And those interested in design for machine learning algorithms, circuit boards, and VLSI are encouraged to apply. Discussion. The APFGP enabled conscious learning theory, and I think it's an AI revolution and go beyond the current limitation of AI using post-selection, and the data are inflated, give you illusion of high performance. But if you have new data, actually the performance I expect a lot worse, because the neural network using data fitting do not generalize well and do not have any mechanism of abstraction and invariance. And the meanings emerge as a conscious action through APFGP, So it's a meaning, it's semantics instead of just handcrafted symbols. A wide acceptance of APFGP for AI might take many years because humans tend to stick to their habits and very difficult for them to go beyond their comfort zones. And I'd like to discuss three bottlenecks. Resistant to this revolution due to our own washed brain, not interested in detailed solutions to fundamental problems of AI. Many people are concentrating on writing papers, but not really interested in what kind of fundamental problems they are facing. Many people, they understand the fundamental problems. In order to write the papers, they don't solve those fundamental problems. And the current lack of education in subjects are required by conscious learning. And as I said, there are 6 disciplines that are required. BMI tried to provide service for the research community. The third one is brain scale on-the-fly learning chips that need to do brain size real-time updating. That's pretty challenging, and this theory can be fully tested if such a VSI is available. Thank you very much. And I'd like to answer your question in the conference. If you are watching this one through YouTube, and feel free to send your question on the comment section. And I tried my best to answer if I could. Thank you very much.